Welcome to our video lecture on periodicity. Our essential understanding for today is that the arrangement of elements in the periodic table helps us to predict their electron configuration. We're also going to look at trends of properties in the elements, and these trends are supported by the arrangement of the elements in the periodic table. Our objectives. First, we're going to even talk about this periodic table thing. We're going to look at the history of the development of the periodic table. We're going to identify different families and groups of the periodic table. We're going to review those blocks, S, P, D, and F. And then we're going to define periodicity and then describe some of the trends of properties that IB likes to talk about. So atomic radius and ionic radius, ionization energy, electron affinity, electronegativity, metallic character, and pH of period 3 oxides in water. Some of these you will have seen already in the first year of chemistry, so atomic radius and ionization energy and electronegativity we definitely do in 10th grade. The rest of these will be new to us. So here's lots of vocabulary that we're going to talk about today, super fast. Most of it you probably already know. There might be a few words in here that are new. If you want to pause the video and look any of these guys up, super duper. Otherwise, here we go. All right, so periodicity is related to the arrangement of elements in the periodic table. And we haven't always had the periodic table. Humans had to develop it over time as we learned more and more about elements and about chemistry. And so one of the first organizations of elements, our first periodic table, was developed by this guy, Dobereiner, and he came up with this law of triads because he looked at lithium, sodium, and potassium that had some pretty cool similar properties, and he took their masses and he averaged them, and he saw that the average of the masses was actually equal to the middle guy, so that the mean and the median were equal. He thought that was pretty cool. Similar for calcium, strontium, barium, similar for chlorine, bromine, iodine, and then he also averaged the 3 lightest guys of each triple, the 3 middle guys, the 3 heavy guys, and he noticed that the average masses of those were similar to each other. So he thought that was pretty cool. And then we discovered more elements, and then the triads didn't quite fit. So then Newlands came along and he said, wait, we have octaves. It's like music. And so he built hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and it was like an octave of elements, and that was really cool. But then, like, they didn't match, so never mind. Mendeleev then came along, and he really was the person who put together the periodic table that we still use today. So some edits, we have definitely discovered more elements since Mendeleev put together his periodic table, but what's amazing about his periodic table is that he actually predicted that there would be more elements found. He was like, there's got to be something here with these masses and these properties, and so pretty cool that he was able to predict the missing elements and where their masses should lie. And of course you can't talk about Mendeleev without a creepy Mendeleev photograph. All right, and then Moseley. Moseley is modern periodic law. So Mendeleev arranged his elements in increasing mass. Moseley was the guy who figured out that actually periodic table elements are arranged by the number of protons. So hydrogen is number 1, not just because it's the lightest, but because it has 1 proton. And helium isn't just the second lightest, it has 2 protons, and lithium has 3, and so on and so forth. So Moseley put together our modern periodic law based on numbers of protons, atomic number, as opposed to Mendeleev's periodic law, where he arranged elements in order of increasing mass. So the periodic table is pretty cool. It is arranged by period number. Period numbers are here going down the y-axis, and these are valence energy levels. So if n equals 1, that means hydrogen and helium only have energy level number 1, N equals 2. Lithium, beryllium, all of these guys have 1, 2 energy levels, and energy level number 2 is their valence energy level, so on and so forth. Group numbers, these are up here. So IB uses 1 through 18. The periodic tables that we use in 10th grade chem, they have A's and some B's. We don't use A's and B's in IB. It's just 1 through 18. So the group numbers that we use, A's and B's, help us find the number of valence electrons. This is not quite as helpful when we're going 1 through 18. But you can skip over to noble gases that are here and just count backwards. 8, 7, 6, 5, 4, 3. And then the transition metals are weird because of the overlapping energy levels. So these guys are the alkali metals, group number 1, and they have 1 valence electron. The halogens, we're going to skip all the way over here. Group 17, they have 7 valence electrons. Noble gases are here. They have 8 valence electrons, except for helium, which only has 2 because it's an energy level number 1. And there's only space for 2 electrons in energy level number 1. Also, we have, so this alkali metals, these are alkaline earth metals. These are the transitional metals, the transition metals. These are the main, these are the inner, and then the inner transition metals also can be referred to as the lanthanoids, because that guy, and then the actinoids are here because of that guy. So kind of a quirky thing about our how the periodic table is arranged. You know how when we draw a map of the United States, it's like this, and then we're like, and here's Alaska and Hawaii, because if we put Alaska and Hawaii where they really are, they wouldn't fit reasonably on a piece of paper. Same thing with our periodic table. So all of these guys should really be right here. So this is 58, 59. It should come right after 57. So we should really split here, shove all of those guys over, and plop these guys up in here. But then we would have a very long, skinny piece of paper, and that's annoying. And so we just chop these guys out and plop them down at the bottom. Kind of like how we chop Alaska and Hawaii out and we put them on the side of a map. They're really not there, but we pretend. Good. So pay attention to those different groups, those different special groups. And then the valence electron numbers come from group numbers. Energy levels come from period numbers. Periods going 1, 2, 3, 4, 5, 6, 7. Groups going 1, 2, 3, 4, 5, etc., etc. All right. So we're also going to chunk our elements into metals and non-metals, and we're going to build a little step ladder here. Dun, 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 dun. Good. So here's our step ladder. Things to the left are metals. Metals are good conductors of heat and electricity because they have lots of free electrons that allow for the movement of that energy. They are malleable and ductile. Malleable means that we can dent them or smash them down. Ductile means that we can roll them or stretch them out into wire shapes. And it's because of the, so this is describing malleability up here. So metals are formed in these lovely little layers of cations. So metal atoms actually release their valence electrons and they float around. And what's super cool is because of the arrangement of these lovely little layers of metals, we can actually shove those layers against each other, which is why metals are malleable and ductile. They're also shiny, lustrous, they're very reflective. It's that photoelectric effect, and they tend to be oxidized. And so hopefully remember this word oxidation. Leo says Gur. Oxidation is losing electrons or protons, and so metals tend to lose their electrons. Non-metals are to the right of our little stepladder line. They're the opposite. They are not good conductors of heat and electricity. They are neither malleable nor ductile. They're not very shiny. And instead of being oxidized, they're going to be reduced, which means that they gain electrons, usually from the metals. And then metalloids are in the middle. Metalloids to memorize. So boron and silicon, germanium, arsenic, antimony, tellurium, and then astatine. These are our metalloids. Not every book describes exactly this group. Sometimes we throw in some other ones, but for IB, these are the metalloids that you want to have memorized. They're semiconductors. Sometimes they're amazingly good conductors, and sometimes they're not. It just depends on the environment that they are in. Sometimes they're very metallish, and sometimes they're not very metallish. Good. So we also talked about the periodic table groups, S, P, D, and F, our blocks, our S, P, D, and F blocks. So I mentioned how the periodic table really ought to be stretched out. Here it is looking kind of stretched out. So we have S, and then P, and then D, and then F. These are the guys that we throw down at the bottom of the periodic table just to make it manageable on a piece of paper. So here are those guys now down at the bottom of the periodic table just so that we can fit it reasonably on a periodic table. So here comes our essential understanding. The arrangement of the elements in the periodic table helps us to predict their electron configuration. I can look at where an element is on the periodic table and I can figure out what its last piece of electron configuration is going to be. So I look at 3s1 and I find 3s block 1, and 3s1 is going to end, this is sodium. This is sodium on our periodic table. I can find 5p, 1, 2, 3, 4, 5. 5p5, I know that that is iodine. 4f2, 4 is down for F. F is here, this is for F. 1, 2, this is going to be cerium. I can do the same but backwards. So I can find xenon, which is 5p6. 5p6. Xenon's right here. I know that its electron configuration is going to end in 5p6. That's xenon right there. Barium. Barium is right here. I know that the end of its electron configuration is going to be 6s1, 2. Barium's going to end in a 6s2. And then gold. Where even is gold? Gold is right here. I know that it's going to end in a 5d. Remember, this is kind of weird. So even though it's period 6, because of that overlapping stuff, we're actually going to have 5d. And it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. 5d9 is the end of gold's electron configuration. All right, so now we're going to talk about these periodic trends. So periodicity, what even does that word mean? Periodicity is these trends in physical and chemical properties across periods and down groups in the periodic table. So things are going to increase going across or decrease going down. This is periodicity. These trends or these patterns in properties that are based on the arrangement of elements in the periodic table. And these are the guys that we're going to talk about one by one. First up, atomic radius. How are we going to find the atomic radius? We actually put these guys into diatomic molecules, and we find how long that bond is, and then we chop it in half, and that's going to be the atomic radius. And then kind of a weird thing, this boundary surface of an orbital. So back to atomic structure. We know that we've got the nucleus, we've got these energy levels, and sometimes we draw them as rings, and it would be very easy to say, haha, valence energy level nucleus, that can be the radius, but in fact the electrons are like all crazy sauce all over the place, and so we humans have arbitrarily chosen 99% probability of finding an electron is going to be the boundary surface of the orbital. We're going to decide that the orbital ends here, and we're going to measure that distance for the radius because 99% of the time electrons are in that space. We can look up our atomic radius in our data booklets, table number 9. Kind of a cool thing about atomic radius, as we get heavier, we get smaller. And we talked about this a little bit at the start of the year. As we have an increase in proton number, we are going to have smaller and smaller and smaller atomic radii because the increased number of protons pulls on the electrons more strongly. We call that effective nuclear charge. Effective nuclear charge is basically that pull of a nucleus on the electrons. ZF is effective nuclear charge, and it's going to be the power of the protons in the nucleus minus this thing of shielding. So shielding is this idea that the inner electrons, these inner electrons, are actually going to shield the outer electrons from the pull of the nucleus. There's that repulsion thing between the electrons, the inner electrons and the outer electrons. And so even though these guys are getting pulled in, they're also getting pushed out. And so the effective nuclear charge is not just the power of the protons, but we're also now going to add this idea of shielding, where the inner electrons are kind of repelling those outer electrons, pushing them out a little bit more. So transition metals don't change too much because they have that constant s orbital. That s orbital doesn't change very much. Table number 9 is again going to give us our atomic radius. Going across, proton number is going to cause things to get smaller. But then going down, our atomic radius gets quite larger, and it's all because the increase in our energy levels. So more energy levels means bigger, but more protons means smaller, but another energy level is going to make things get super big again. Ionic radius. Ionic radius, now we're making things into ions. So either cations that are positively charged or anions that are negatively charged. So I love this image because it shows us in gray is the atom, and then the color is going to be the ion. So we can see that the atom to the ion, the pink guys that are our cations, are getting smaller. Cations are going to get smaller than the parent ion, the parent atom. That number of protons, fewer electrons, less shielding, we're going to have a stronger effective nuclear charge. That's opposite when we have our anions. So again, gray is the atom. And here for our anions, the blue is going to be our ion or anion. And we can see here that we get bigger. So from atom to ion, we get a little bit bigger. Because there are more electrons, there's more repulsion in that valence energy level, and so these guys get just a little bit bigger. Table 9 is our data table for showing us, in our data booklet, data table for showing us ion radii, and a little mnemonic device that might not help you, because I don't know if you even know what AOL is, if you've ever even heard of that. But you can remember AOL, which used to be America Online, I think is what it stood for, but it's also anions, and ions are larger. So you can remember that way if you need it. All right, ionization energy. This is the minimum amount of energy required to remove an electron from a neutral gaseous atom in ground state. So lots of little pieces of energy, vocabulary here. Energy, how much force, how much energy is required to remove an electron. So we're taking electrons away, which is why it's called ionization energy. We're turning these atoms into ions. But we're going to put it into a standard kind of state. It's going to start neutral. So we're starting at an atom, and it has to be in gaseous state, and it's also going to be in ground state. So we don't have excited electrons that we zapped with our Bunsen burners, but we're starting at ground state, electron configuration, gaseous state, and starting at neutral atoms for first ionization energy. We're going to measure that in how many kilojoules per mole. So IB doesn't really like to use a slashy sign, kilojoules per mole. Instead, we're going to show moles to the -1. That means that I have moles in the denominator, kilojoules in the numerator, kilojoules per mole, kilojoules per mole, kilojoule, mole to the -1. First ionization energy is going to be in table 8. We're taking, again, that neutral atom in gaseous state. We're going to take an electron away from it. How much energy is needed to make this happen is what we have in table 8. Second ionization energy, if I take this guy and I try to take another electron away from it, that's going to be second ionization energy. So some interesting patterns going on here. So we're going from hydrogen to helium. Way more energy needed to remove electrons from helium than from hydrogen. If we notice all these top guys, so neon, argon, krypton, xenon, what kinds of elements are those? Oh my gosh, those are our noble gases. So because the noble gases have full valence energy levels, they have all the electrons that they need in that outermost energy level. They are most stable, and because they are most stable, they don't want to give those electrons away. And so a lot of energy is needed to remove electrons from the noble gases. If we look at the bottom points, we have our alkali metals, and these guys all have only one valence electron, and that's super unstable to have only one, and so they basically just want to give it away. So not a whole lot of energy needed to remove electrons from the alkali metals. Another trend to look at, notice that helium is the most, and then neon, and then argon, and then krypton. So we definitely have a decrease going across, and this is because the smaller the atom, so helium is 2 protons and 2 electrons, the smaller the atom, the less distance between the nucleus and the electrons, the greater that effective nuclear force. And so because these guys are so small, these electrons are held super tight. A lot of energy is required to remove electrons. If we're talking about helium, neon, argon, krypton, so krypton now is in period 4. So krypton's got a bunch of protons in the nucleus, but it's also got 1, 2, 3, 4 energy levels. And so these electrons, even though it's full and stable, that distance, and then also all of that shielding happening here, 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 is going to reduce the strength of the pull between the protons in the nucleus and these valence valence electrons. So it's just easier to remove these electrons from the bigger atoms. So bigger atoms are always going to have lower ionization energies. The bigger they are, the farther away the electrons, the less that force of pull, the less the effective nuclear charge between the protons in the nucleus and the electrons in that outermost energy level. Good, good. All right, so electron affinity is almost the same but backwards, but really almost the same. So electron affinity is the energy required to remove an electron from a singly charged negative ion. So if I start with a negative ion and I take that negative away and send it back to neutral, how much energy is needed to take that electron away? But it can also be, so I can flip it and go back the other way, is the amount of energy released. So not required, but the energy released when things are more stable, when those electrons are gained. So especially if we're talking about like our halogens, so fluorine has 7 valence electrons. 8 is so much more stable than 7. And so when this guy gains that extra electron to become fluoride, and it has that full valence energy level, it is more stable. And so this amount of energy is released because of the increase in stability of that particle. If I wanted to take that electron away from fluoride and turn it back into fluorine, I would need to add 328 kilojoules of energy for every mole of fluoride ions that I was trying to do that to. So these are saying the same thing, but just opposite. So how much energy do I have to add to steal an electron away from an ion, a -1 charge anion? But it's equal to the energy released when that 1 electron is gained and makes especially our halogens, just that little bit more stable. So electron affinity, ionization energy. Ionization energy, we're going from neutral to +1. Electron affinity, we're either going from neutral to -1, or we're going from -1 to neutral. This would be a release of energy. It would be a negative delta H because energy is being released into the environment. This would be positive, positive because we're absorbing energy to make that happen. So ionization energy, electron affinity, super similar, just kind of backwards like this. And here is our graph for this. Halogens have the greatest electron affinity because that one more electron takes them to that full valence energy level, and that's a very happy place for them to be. Who's the lowest? Well, we've got lots of our noble gases once again, and then our metals are not much higher than that. These metals do not want any more extra electrons. Noble gases also don't want any more extra electrons. They are already full. They don't need any more. All right, so electronegativity. Similar, we're still talking about electrons, but now we're talking about atoms that are in bonds. So atoms that are in bonds, covalent bonds, are sharing electrons. Electronegativity is the attraction that an atom has for that shared pair of electrons in the bond. So if we're talking about like maybe carbon and oxygen in CO2 molecules. So they're sharing these electrons between them. The question is, are they sharing them equally, or is oxygen perhaps just a little bit more electronegative than carbon? It is, in fact. So oxygen is a little bit more electronegative than is carbon. And so what's going to happen is these electrons that are technically being shared are actually going to get pulled closer to oxygen. These electrons that are being shared are going to get pulled closer to oxygen because oxygen is more electronegative than is carbon. This is not really measured in like a kilojoule per mole. It's not measured. It's a totally arbitrary scale that was made up by Linus Pauling back in 1932. He decided that fluorine, most electronegative of all of our elements, should be 4, and then everything else is just scaled relative to fluorine. Fluorine is the most electronegative of all of our atoms. It is small. So fluorine is the smallest of our halogens, and also if we're talking about like F trying to share with maybe lithium, and I know that this is technically an ionic bond, but pretend like they would share, fluorine would basically take those so close they would be here. Lithium wouldn't really get them at all. Because fluorine is small, it only has 2 energy levels, and it's only 1 away from having that full valence energy level number 2. It's going to pull super, super strong. The bigger our atoms get, the less electronegative they become, and also more to the left of our periodic table, the more metallish you are, the less electronegative you are. All right, metallic character, this is just how metallish are our elements. Metals tend to have very low ionization energies, they have low electron affinities, they have low electronegativities, and they tend to lose electrons. They're more likely to be oxidized. The most metal of all of our metals is big and to the left. So the bigger you are, and francium has 1, 2, 3, 4, 5, 6, 7, whoa, I drew too fast. 7 energy levels. The pull of these protons, there's a lot of protons, but this one valence electron is so far away from the protons of the nucleus that there's almost no force left. So francium or francium, depending on if you live in Britain or the United States, it's basically going to give its electron away. It's like, take it, I don't even care. So metallic character, most metallish of all of our metals is francium, and then the least is going to be helium because it's so tiny and has a full valence energy level. So metal and nonmetal oxides. Oxides are compounds that have something and oxygen. It's going to be an oxide. So if I take sodium and oxygen, I put them together, oxygen is going to take electrons away from sodium. Oxygen has 6 valence electrons. It wants to get to 8. It needs 2 more. Sodium only has 1 to give away. So I actually need 2 sodiums to make that 1 oxygen have a full valence energy level. So sodium oxide is Na2O. Calcium has 2 valence electrons. It's willing to give away both of those, which are exactly the 2 that oxygen needs. And so calcium oxide is just a CaO. When I take this sodium oxide and I combine it with water, this is going to form bases. Bases are the opposite of acids. They have pHs greater than 7. So I'm going to take that sodium oxide, I'm going to add it to water. What's going to happen is we're going to reshuffle things around and we're going to get sodium hydroxide. Hydroxide is a super common polyatomic ion in bases. So sodium hydroxide, and to balance this, we're actually going to have 2 sodium hydroxides. This is a base. So if I take a metal oxide, sodium is an alkali metal, and I combine it with water, we're going to make a base, sodium hydroxide. I can do the same thing with calcium hydroxide. We're going to end up with calcium hydroxide. I have 2 hydroxides because calcium's charge is a +2. Remember that I can give away those 2 valence electrons, so +2 calcium, 2 hydroxide polyatomic ions, and again we have a base. That hydroxide polyatomic ion is letting us know that we've got a base. pH is going to be greater than 7. Good? Good. What if I take a non-metal oxide and I react it with water? So let's say that I have SO3. This is sulfate, sulfur trioxide, and water is going to combine to make H2SO4. 2 H's, 1 S, and 3 + 1 more SO4. This is sulfuric acid. That H in the front lets us know that we've got an acid because this polyatomic ion is called sulfate. 8 turns into ic when we name our acid, sulfate to sulfuric. If I take sulfur dioxide, SO2, and I combine it with water, we're going to have similar but slightly different 2 H's, 1 S, and 1, 2, 3 O's. This is going to be sulfurous acid because SO3 is the polyatomic ion sulfite, and when we name our acids, ite turns into us. I can also take carbon dioxide and add it to water. This is what we do when we make carbonated beverages. So CO2, carbon dioxide, and water is going to make 2 H's, a C, and 1, 2, 3 O's, and this is carbonic acid because this polyatomic ion is carbonate, and once again 8 becomes ic when we're naming our acids. All right, so we can look at the trend of pHs of our oxides. IB especially loves period number 3, and so these are going to be basic and these are going to be acidic. pH less than 7, pH greater than 7, because these are bases and these are acids. But what about in the middle? In the middle we have aluminum oxide. Here's a crazy, crazy thing. Aluminum oxide is going to be both acidic and basic, depending on if the environment that I'm adding it to. So this property of being both acidic and basic, being able to have acidic properties and basic properties at the same time, this is amphoteric. This amphibian or ambidextrous, those of us in biology know that amphipathic, I just lost that word. We have amphipathic phospholipid molecules in our membranes. They are both hydrophilic and hydrophobic. So this prefix amph tells us both. So things that are amphoteric are both acidic and basic. So if I take some aluminum and I make it kind of with a base or with an acid, we're going to end up with different things going on. It can be both acidic and basic depending on the environment that it's in. So more basic, more acidic, and then this guy in the middle can choose which way to go. All right, so we have achieved our lecture objectives here on periodicity. We reviewed the history of the periodic table. Mendeleev is really the guy that we talk about the most. We looked at those different families and groups, the alkali metals, alkaline earth metals, halogens. Remember that going down the periodic table, this is telling us our energy levels, and then going across the periodic table, our groups, this is giving us valence electron numbers. We talked about those blocks. S is here, P is over here, D is here, and F is on the bottom, but really it should be like right there. And then we defined periodicity and we described some of those trends: atomic radius, ionic radius, ionization energy. We're removing electrons, electron affinity, we're adding electrons, electronegativity, we're pulling shared electrons, metallic character, how metallish are you? And then we talked about the pH of those period 3 oxides in water. Good work, my friends. I'll see you next time.